Welcome back, everyone. Today we're jumping right into a brand new explainer, and we are tracing the fascinating evolution from C's bare metal procedural logic all the way to Java's highly structured object-oriented safety net. So if you've ever found yourself wondering how our computing logic actually translates from physically touching the hardware to safely sandboxing our code, well, you are absolutely in the right place.
Think of this whole explainer as building a bridge. To cross from that basic procedural logic into the world of language security, we're going to follow this structural blueprint. First up, two paradigms, POP versus OOP. Next, fundamental logic and input. Then, we'll hit the power of iteration, organizing data and functions, and finally, the pointer security divide.
All right, let's kick things off with Section 1, two paradigms, POP versus OOP.
So to understand this bridge we're building, we really have to figure out where it starts. C is built entirely on procedural-oriented programming, or POP for short. In this paradigm, your program is essentially chopped up into standalone functions. It acts as a direct, top-down list of instructions. You are literally telling the computer precisely what to do, step by step in a superlinear fashion. And hey, it is incredibly efficient. But as your programs start to grow, managing these endless lists of instructions, it can get pretty complex. To keep from getting totally lost in the weeds of granular code, we can actually categorize our examples into broader conceptual themes. It helps us see the forest for the trees, right? Whether you're coding in C or Java, you're always dealing with these four main pillars. You've got selection logic for decision-making, iteration for those repetitive tasks, modularity for organizing your code, and memory management for handling exactly where your data lives. Just keep this mental map in your back pocket as we move forward.
Moving right along to Section 2, fundamental logic and input.
Right at the very beginning, the input stage, the architectural difference between these two is just striking. Let's say you're in C and you want to take in two numbers. You just call a simple procedural function, scanf. Easy enough. But in Java, oh no, you can't just politely ask for a number. You actually have to instantiate the scanner class. You are creating a whole entire object whose sole purpose in life is handling input. It's notoriously verbose, for sure, but even for the simplest data intake, Java is forcing you to think structurally. You have to think in terms of objects and classes from line 1.
But here's the catch. While those input methods differ drastically, the core selection logic acts as a universal bridge. So if you're trying to figure out, say, the largest of three numbers, both C and Java rely on the exact same universal logic, the classic if-else statement. The paradigm might completely change how you package that logic, but the fundamental flow of asking, hey, if this condition is true, do X, otherwise do Y, that is identical whether you're in a procedural or an object-oriented environment.
Which brings us to Section 3, the power of iteration.
Let's break down the math logic here, using prime numbers. And don't worry, we won't just dump raw code on you. To check if a number is prime, both C and Java start a loop, and they usually test numbers from 2 right up to half of our target integer. Inside that loop, they use the modulo operator, that little percent sign, to find the remainder of the division. If that remainder hits exactly 0 at any point, boom, a flag is triggered. That means the number is divisible by something other than 1 and itself, so it's definitely not prime. And the really beautiful thing here? This little loop and modulo dance works exactly the same in both languages.
We actually see a very similar mini-narrative of mathematical manipulation when we check for a palindrome, a number that reads exactly the same forwards and backwards. First off, you grab the last digit of the number using modulo 10. Then you mathematically build a brand new reversed number by multiplying your running total by 10 and adding that remainder you just found. Finally, you just divide the original number by 10 to strip off that last digit, and you repeat the loop. It's this brilliant little pattern check entirely handled by universal mathematical operators.
And honestly, whether you're calculating the sequential logic of a factorial using a while loop, or generating a Fibonacci series using a for loop, the core takeaway here is consistency. Both C and Java rely heavily on these exact same core control structures. In fact, the syntax for a while or for loop is virtually indistinguishable between the two. The underlying engine of iteration is universally shared, even if the vehicle it's powering looks totally different on the outside.
All right, let's pivot to Section 4, organizing data and functions. This is where we see a pretty dramatic architectural split.
And this difference right here perfectly illustrates that crucial turning point between POP and OOP philosophies. Think about it. If you want to represent a student in C, you use a structure, or a struct. But a struct only groups data, like a roll number and a name. It's really just a container. Java, however, uses classes.
A class doesn't just group the student's data, it also groups the methods, the actual functions, that operate on that data. So the behavior and the information are bound tightly together in one neat package.
This idea of encapsulation really cascades through everything. For instance, arrays in C are handled completely manually. They're just raw collections of elements sitting in memory, and C divides all its logic into those standalone functions we talked about earlier. Java, on the flip side, prefers everything neatly packaged. It encapsulates both the data and the functions that manipulate that data right into objects. So in Java, you don't just have a plain array, you have an array object that comes fully equipped with its own built-in tools.
And finally, that brings us to our climax, Section 5, the pointer security divide.
So C provides programmers with an incredibly powerful tool for memory management. I mean, it's a tool that forms the absolute bedrock of operating systems and embedded hardware. Yet Java takes this exact same tool and outright bans it. No way around it. So why would they do that?
Well, that tool, of course, is the pointer. In C, pointers allow you to directly access and manipulate raw memory addresses. It is literally the ultimate bare metal power. You can point directly to exactly where a variable lives in the computer's physical memory. Java, however, explicitly excludes pointers. It completely and deliberately hides memory addresses from the developer.
The source material actually puts it perfectly, stating that Java does not support pointers in order to provide a, quote, secure runtime environment and to eliminate complexity. Java's entire core philosophy prioritizes safety above all else. Think about it. If you can't access direct memory addresses, you can't accidentally or maliciously, for that matter, overwrite critical system memory. It eliminates a massive source of bugs and security vulnerabilities, essentially sacrificing that raw hardware control for a highly secure, simplified sandbox.
So this really leaves us with a final question to ponder. What is the ultimate trade-off for a programmer? Do you prefer the paradigm of C, which completely trusts the developer with ultimate memory control and bare metal performance? Or do you lean toward the paradigm of Java, which explicitly restricts that control to ensure a highly secure, much less complex environment? Honestly, there's no wrong answer here, but understanding this trade-off is absolutely key to mastering language design. Thanks so much for joining me on this explainer today, and as always, keep exploring.